Hello, my name is Homero Barreto. My Panther ID is 613-9408, and this
Uh,
is.
Hello, my name is Landi. My Panther ID is 622-6932, and this is the lab experiment 1 for the class EEE4304. I'm going to share my screen in order to show you guys the experiment that we're going to be going over during this class, this lab experiment. So experiment 1 basically deals with the op amp, the inverting op amp. And on the first section of this experiment, we're going to be theoretically analyzing it, simulating, and implementing in a proto board this circuit above, and testing for different resistors, quotients, the gain, and how it behaves. On section 2, we're going to be designing an inverting amplifier of 100 gain at 100 hertz, and then analyzing the slew rate of the op amp, and then going over the current limitations that the op amp has. And on the fifth circuit, you guys asked us what's wrong with this circuit. So starting with this question here, you can analyze that this is an inverting op amp, and it's applying a 2 volts gain on the output. And if you analyze a regular op amp, it has a 20 milliamps input current limitation. And if you analyze the circuit right here, you're going to see that the current that is flowing through the circuit here is bigger than 20 milliamps. So this resistor's quotient wouldn't allow us to get the 2 volt gain that we would actually have with a bigger resistance because of the current limitations of the op amp. So starting with section 1 right now, this is the PDF file. It's basically a theoretical analysis of this experiment. So drawing this circuit again and getting R2 and R1 and considering ideal op amp, we can check that the V plus, which is called Vx here, and Vy are equal. Vi is grounded, so it's equal to 0. So Vx is 0 too. And the current entering the op amp is theoretically and ideally speaking, it's 0. So analyzing the transfer function via node analysis, we can check that the transfer function of this circuit is R2 over R1. Based on the gains that the section 1 is asking us to do, we got a gain of 10 based on this expression, and keeping R1 as 100 ohms for every single experiment. We just change R2 and get the gain that we want. There is a theoretical limitation and an implementation, also a limit in the implementation because we don't have bigger resistor values to get this kind of gain. So we'll probably restrict ourselves to this section right here, to this column here. To the simulation part, this is the circuit that we simulated on PSpice. The op amp uses an ideal op amp, so that's why we're not going to be able to analyze the slew rate and other aspects of the circuit, just the gain itself based on the AC SWIP. So applying a resistance quotient that we mentioned before in the PDF file and putting the resistance quotient to gain a 10 volt gain, we observe that in an AC SWIP, we're going to have a 10 volt gain based on a 1 volt input that we're putting right here. And then changing this quotient of resistances, we can get different values of gains. So here we have 100 gain, 1,000 gain, and 10,000 gain, which was the implementation limitation because we don't have higher resistances. Okay, so we can observe the behavior since it is only a resistance quotient, it's not related to frequency, so it's going to be a constant gain throughout all frequency range. Okay, so now Homero is going to go over the implementation section of the experiment.
All right. So here it is. So here we can see the first circuit designed, which is a circuit with a gain of 10. So this is our physical circuit design, and this is the function generator that we'll be using throughout the experiment. In this first portion, we used a 0.1 volt peak-to-peak amplitude, and then this is our oscilloscope that we'll also be using throughout the experiment. And here we can see that we have 100 millivolt initial input, which was the amplitude, and then our output was a 1.425 volt output, peak to peak. So here is our Bodie plot, where we can see the minus 3 dB frequency at 17,571, and it's pointed right here. This is the Bodie plot going downwards. And then the sort of process is repeated by changing the resistor value to match the gain necessary for the experiment. So that is continued throughout this first portion. And here's the other minus 3 dB portion and gain of 1,000. So here we'll see that we use a 0.05 volt peak to peak and that our oscilloscope is clipping. So here we'll realize that the gain of 1,000 volt, the requested gain of 1,000 volts was not not able to be met. Instead, we got a gain of 426.58. So that means our highest possible gain that was requested that we actually were able to do was 100. So we weren't able to do 10K or 100K. Here we can see that the amplitude used for 0.10 volts, the output we got was 1.425, which gave an actual gain of 14.25. We were able to determine that this is probably due to a offset voltage in the circuit that is altering the actual output. So we got slightly higher, and this is also shown here when attempting the requested gain of 100, where we actually got an actual gain of 142.84. So in section 2, we were asked to build a minus 100 gain circuit amplifier at 100 hertz. So we were able to do that, where we can see that at frequency of around 100, 95.09, we got a gain of 103.21, which shows that it was able to be done. And then you wanted us to test if we were able to clip it. So we were able to do so at 130.21 millivolts. That's where we see initial signs of clipping at the base right here. And then we were able to increase that clipping by going to 340.16 millivolts, reaching the circuit limit of the MIDAC and voltage limit, so which is 21.329 volts. And we can see that it is clipping on both sides. That's where it initially starts clipping on both sides. And then finally, if we increase the voltage by a significant amount to 5 volts, so a 0.34 volt jump to 5, we were able to see even more significant clipping. So it also was able to reach the 21.329 voltage limit and was more clearly clipping on both ends. So section 3, we were asked to be able to test the slew rate and see the slew rate characteristics. This was done by giving a significant frequency of 10K hertz and a significant amplitude of 5 volts peak to peak, while also providing it as a square wave. That is shown here, where we were able to zoom in and be able to more clearly determine the voltage minimum and maximum of the circuit, as well as the rise time of the square wave. Yeah. So here we will to show that it's 40 microseconds. Then the minimum was 10.66 volts, and the highest voltage was 10.05 volts. And this was done again by altering the amplitude to see a different result, which was 8.0 volts peak to peak, still keeping the 10K hertz and the square wave. Here we were able to get the minus 10.44 minimum and maximum of 10.67, and the rise time stayed the same at 40 microseconds. The slew rate, we were able to calculate that by doing the V maximum minus the V minimum over the rise time. So that is shown with this equation right here. And we were able to get a slew rate for the initial test of 0.511775 and the second test of 0.52775, where the minimum slew rate of an op-amp of LM741 is 0.5. So we were able to get something that showed that that was possible to reach. As for section 4, the instructions stated to use a value of lower the value of R2, but since we used a value of R1 that was 100 ohms, which was too high to be able to do a current limit, we instead lowered both the R1 and R2 values. And by doing so, we were also using the equation 20 milliamps equals V out minus V in over R1 plus R2 to be able to find a voltage and resistances that was better able to show the current limit test. So this is the physical current limit circuit that we did. It's essentially the same as the previous circuits, just with the lowered R1 and R2 value. And the voltage applied was 0.45 volts at 100 hertz. And this shows a significant clipping here due to it trying to draw so much current with the lowered resistance we used, which were an R1 of 7.5 and an R2 of 15 ohms. So if we applied a 0.45 volt peak to peak, we should have expected a 0.9 due to it being a 2-gain circuit, but we weren't able to get even close to that, showing that it is being current limited. Then we did applied a higher voltage, and it did the same. We weren't able to get the 2-volt gain that we were supposed to receive. And that was continued in this third part where we lowered it instead, and still the same. So here we can see the amplitudes applied using the new resistors, and these were the actual outputs we received, while this was supposed to be the expected ones, which were much higher, and we weren't able to even get close, showing that we were indeed able to current limit the circuit as requested. But it instead required the changes of lowering the R1 value as well as the R2. Also, something I want to add was that the MIDAC has a limit of 2 milliamp supply current. So even then, we were asked to reach a 20 milliamp limit, but the MIDAC only gets to 2 milliamps anyways. And that's what we did for our Activity 1 lab.
Thank you, everyone, and stay safe.